So we're starting, Allison, chapter 12. It's a big jump all of a sudden. I skipped chapter 10 and 11. They used to be part of the course. What? Yeah, but they pulled them out because they felt Science 10 was too full. They're not on the provincial, so although they're nerdily interesting, if we had time, I'd cover them, but that's one way that I can pick up some time. Jasmine, you're going to find, if you look at the textbooks, it's readable, much more... What am I hearing there? Is that a beep somewhere? Is that from next door?
Probably so.
Okay. You're going to find that you can study from the textbook much easier, I think, in this stuff. Anyways, let's jump on in. Continental drift. Say what? Continents, the big land masses on Earth. Drift, to slowly move. It turns out that the continents drift, and this was only accepted in the 1960s. What are the key ideas? Key idea number one, the Earth is composed of layers. Earth is composed of layers. And Earth's outer layer has moved. Earth's outer layer has moved. In fact, we call them plates because they don't quite line up with the continents. The plates of Earth's outer layer have moved. Can I get my cursor to appear there? Having trouble. Continuously. And Julie, the reason this was such a revolutionary idea is, listen to what I'm telling you. I'm telling you, solid rock moves. No, it doesn't. Yes, it does. No, it doesn't. Yes, actually, we now know that solid rock moves. But Courtney, it moves very, 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 very slowly. And it really wasn't until we had fancy schmancy satellite technology that we could actually measure the movement. But once we did and confirmed that it does, holy smokes, it explains a lot. So this movement explains many of Earth's geological features and events. So here is the continental drift theory. This is what we believe. We're calling it a theory, but it explains enough that I'd almost be willing to call it fact. We believe that many millions of years ago, hundreds of millions of years ago, all of the continents were once joined as a single supercontinent. And we give this a name. We call it Pangea. That's P-A-N-G-A-E. Can I get it to a... Come on. Stop right there. Pangea. Okay? Matt says, prove it. Oh, well, here's our evidence. You may have noticed, looking at a globe, that it certainly seems as though South America could fit right in there like a jigsaw puzzle. And that Africa could fit right in there like a jigsaw puzzle. So part of the first evidence for this, already 200 and 300 years ago, map makers started to speculate. So evidence number one, the jigsaw fit of the continents. By the way, here is Pangea and how the continents kind of fit together. Jig-Sam, jigsaw. Wow, there's a flip that for some reason. So that's evidence. You can even put a little number one there. What else? Well, we have found the same fossils on several different continents. And nowadays they're separated by oceans. How the heck could the same animals be on different continents separated by oceans? Alex, maybe they weren't separated by oceans a long time ago. Maybe it was part of the same land. You want an example? Example, one of the big ones is the mesosaurs, and I wrote, see page 508. There's a whole bunch of different pictures there. Taylor turned there. Those are the color pictures that I just can't reproduce. I've tried. So that's piece of evidence number two. What else? So piece of evidence number three The same type of rock outcrops on separate continents. So even though the continents are separate, the types of rock are identical, almost as though they were once part of one big uber rock that got split in half, or split in third, or split up. Okay. What else? Piece of evidence number 4. Here's the fancy word. Paleoglaciation. Can you see the word glaciers in there? We can see the carving of the earth evidence that glaciers leave behind. We see them up here, certainly. But we see evidence of glaciers in the tropics. Can glaciers exist in the tropics where it's really, really hot? No. Maybe those areas once weren't in the tropics. Maybe those areas were once much further north or south where ice could exist. The glaciers carved them out, and then they drifted to the tropics. So, evidence of ancient glaciers on continents of the southern hemisphere, where it's hot, while at the same time we know from the records that there was no evidence on the northern continents. Maybe because the northern continents many millions of years ago were further south, and maybe the southern continents were further north. So, the equatorial regions where it's really, really hot, those can't support glaciers. But when we look at the land areas and the mountains that have been carved out, hey, those are exactly what it looks like when glaciers have carved them out. Either ice melted at a different temperature back then? No. Oh, maybe the continents were at a different temperature because they were in different locations. Where does coal come from? Does anybody know? Okay, it comes from the various sources, but the main one is if you have huge forests, and when the trees rot and decay, and then they get covered by dirt, it gets pressed down and it turns into coal. Coal comes from huge ancient forests that have rotted. Where does coal come from? Huge ancient forests that have rotted. You know where we find a lot of coal? Boy, did I spell that right? Antarctica. From what you know of Antarctica, are there huge forests in Antarctica? Could there be, right now, huge forests in Antarctica based on where it's located? So, possible explanation, maybe it wasn't always there. Yep.
Could it have used to be a warm location?
So well, there's two possibilities. Possibility one, Matt, is maybe the Earth used to be way warmer. Possibility two is maybe Antarctica was in a warmer location and drifted. Those were the two competing theories. Yep.
If all of this happened and everything is separated, maybe there's a possibility it could rejoin.
Maybe Mr. Dueck has a video of what the Earth might look like in 100 million years. Can you make sure I show it? So, either the Earth's climate and temperature was, and by very different, I mean really different, like, holy smokes, you're having ice in the, wait a minute, how can you have ice on the equator but also have Antarctica warm enough to have snow? It's either the Earth's really, warm enough to have forests. Either the Earth used to be really cold before or really warm before, so I'm leaning towards continental drift, but we have to be able to explain how on Earth continents, rock, can move. And this brings us to the theory of plate tectonics. One of the big proponents, Canadian. So in the 1960s, they said, we can explain how continents can move. And we think we have the mechanism. We now know that the Earth's surface is broken into large, and by large, think North America-sized large, although some are smaller, but huge, movable slabs of rock called tectonic plates, which is why we call this theory plate tectonics. How do we know that? Well, there's some evidence. First of all, during World War II, submarines were becoming important, and so military from various countries started using sonar and radar to map the ocean floor. World War II was terrible, but some very good science was done in World War II for desperate survival reasons. Splitting the atom bomb, terrible and good because it gave us nuclear power. Lots of good science there. Oh, and mapping the ocean floor. And here's what they noticed. Holy smokes, when they mapped the ocean floor, in the Atlantic, there's a ridge of mountains. In fact, we call it the Mid-Atlantic Ridge. And it goes all the way around the globe. This is an underwater mountain range, and it extends about 8,000 kilometers. It's very large. You can find it on Google Maps, for that matter, if you want now, because we have all this nice, fancy, schmancy technology. Oh, for what it's worth, we now know that these mountains are volcanic. Then, when they took samples, dropping big buckets, actually dropping big scoops and drills, and they drilled into the ocean floor around these ridges, they noticed something really strange. So I got to go into a bit of an explanation, but bear with me, Max. Here we go. They noticed something called magnetic reversals. So, rocks on the ocean floor contain some iron. Iron is magnetic. And we can measure the magnetic fields formed by this iron using a magnetometer, a magnetometer, if you want to think about it, but it's pronounced magnetometer. So, Alex, here's what happens. When the magma from the ocean floor, when the liquid magma bubbles up, it hits the ocean water and it very, very quickly hardens. But before it hardens, while it's still liquid, the iron in the rock has a chance to orient itself on the Earth's magnetic field. It points north, just like a compass. However, if you move further out from the Middle Atlantic Ridge, now the iron is pointing south. And if you move further out, you come to a band where the iron is pointing north again. And if you move further out, you come to a band where the magnetic field, where the iron is pointing south again. And this continues for quite a while, Tyra, where you have these alternating bands of the iron before it hardened pointing north and the iron in the rock before it hardened pointing south. We can measure this using a magnetometer. So the conclusion, first of all, Julia, and you might not have known this, Earth's try that again, Mr. Dueck. North and South Pole swap. And there's still some debate as to why, but it appears that every few 100,000 years, all of a sudden what we think of as north becomes south, and what we think of as south becomes north, based on, in terms of which way a compass would point. All of a sudden, and by all of a sudden I mean over a few hundred years. Wait a minute! My compass used to point that way. Now it points that way. By the way, word of the day, the study of magnetic properties of rocks is called paleomagnetism. Paleo, rock, magnetism, magnets. So, I have the color picture. You guys don't. I think this picture might be in your textbook. Sort of on page what? 512? 511? Turn the page, 512. Okay. So, Page 512. Turns out, and you can kind of imagine just by pushing your fingers together what happens as the sea floor spreads apart, as the younger molten magma keeps bubbling up, it forces the older rocks further and further apart. The older rocks are found further away. The youngest rocks are found closer. Harry Hess, in 1960, he suggested that as magma rises from beneath the Earth's surface, it breaks through and cools when it hits the ocean. And as new magma continues to bubble up, it continues to slowly push the ocean floor outwards. This is one of the mechanisms, Jasmine, for how we believe plates drift. They're getting a push in the mid-Atlantic ridge. The oldest rock, center of North America and center of Europe. Youngest rock, right along the mid-Atlantic ridge. And in many places, it's still being created. There are still active volcanoes. I don't know if I still have the video or the photo, but there's a spot in, I believe it's Iceland, where you could literally swim right along the mid-Atlantic ridge, and with your left hand, you're touching the North American plate, and with your right hand, you're touching the European plate, because it's split right there and slowly moving apart right there. I'll try and find that video again. So, convection currents, all right. What do you guys know about heat or hot air? Hot air what? What's the saying? Well, hot magma also rises. And the magma is hottest in the center of the Earth, so that rises up. As it cools, it gets pushed out because there's more hot magma being pushed up. Now, as it gets pushed out, something happens on the ends. We'll talk about that later too. But for now, in the middle, we have a spreading oceanic ridge. So, here's our summary. Here is Hess's evidence for the seafloor spreading. Okay. The Earth is like a bar magnet, and it has two poles, north and south. That's how compasses work. New ocean floor forms when liquid magma from under the Earth's surface rises, hardens, and cools at an ocean ridge, but there's always new magma pushing up from below, so it pushes the older rock away from the ridge. The further away, Jasmine, you go from the mid-Atlantic ridge, the older the rock will be. But we have noticed this strange phenomenon. So the magma is molten basalt, other rocks as well, but one of the rocks is basalt. And this is a dark rock that is very rich in, what's Fe on the periodic table? Iron. You can write the word iron, but since I can write it with two letters, I'll do that. As it cools, it becomes magnetic because the iron lines up to match the Earth's magnetic field. In fact, the magnetic materials in the hardened basalt are like tiny compass needles. And they align with the Earth's magnetic field. They point magnetic north. However, Earth's magnetic poles reverse of, you know what? Shouldn't be the word of, should be the word over hundreds of thousands of years. Why? We're still working on that one. There's various theories. But they do. We can measure it in other rock as well, where suddenly, oh, the iron's pointing the other way. Minerals in the rock keep the magnetic alignment they had when the rock cooled. So, some portions of the rock will have normal, here's your fancy word, polarity, which way they point, and some will have reverse polarity. And it turns out they form stripes like that. We call it magnetic striping. alternating bands of normal and reverse polarity. These surround ocean ridges. So put that all together, Matt, and it suggests that in the mid-Atlantic, Earth is getting pushed apart, and it's happening over millions, maybe more, of years. The pattern of magnetic striping is the same in rocks on either side, so they pair up, which suggests that those two pairs of rocks are about the same age because they were pointing the same way when the Earth magnetic field was that way. So, if we're constantly bubbling up from the middle and getting pushed apart, where will the oldest rock be? Closest to the ridge or furthest from the ridge? Okay, makes common sense, but we need to know that. So, ocean sediments are thicker and older the farther they are away from the ridges, because the oldest rock furthest from the ridge has had more time to accumulate. The continents in the middle are really thick. But on the edge of the Mid-Atlantic Ridge, the rock is thin enough that the magma can still break through. In the 1960s, a Canadian geologist named J. Tuzo Wilson, what a great middle name, wrote a paper, and he combined seafloor spreading, paleomagnetism, to explain continental drift. Here's what he suggested. He then also said chains of volcanic islands like Hawaii were formed when a tectonic plate, because it's getting pushed apart by the Mid-Atlantic Ridge, passes over a geologic hotspot. Now, a hotspot is where magma rises to the Earth's surface. Once it gets to the Earth's surface, it's called what? Lava. Again, Sage, you understand how controversial this was, because what they were saying in the 1960s is, hey people, rocks move. Wait a minute, we have an expression, solid as a rock. Rocks don't move. Yeah, they do. But it's just really, 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 really slow. How slow? Slower, significantly slower than your fingernails grow. Very slow.